of more than one variable. So that's section 1.10. Those are the two things we're going to cover today. I've also got here the courseworks to hand out to you. So I'll be handing out those at the end, and I'll say a word or two about those. And some of the questions in there are based on this material here, and it's a good setting in which to look at partial derivatives and to see it doing kind of real, genuine work. Okay. Okay, so let's begin in section 1.9 and Taylor's theorem. So you're already aware of Taylor's theorem for functions of a single variable. Okay, so Taylor's function for functions of a single variable provided a way to approximate any well-behaved function by certain polynomials. Okay, and the more terms you took into the polynomial, the more accurate the approximation was. And the coefficients of the polynomial, or the power series, if you like, the coefficients came from the derivatives of the function evaluated at the base point, if you like. Okay, so just to remind you of that setup for functions of a single variable, okay, because it's quite similar. We're going to be generalizing that to functions of more than one variable. So Taylor's theorem for a one-variable function f of x allowed us to write f as, so evaluating the function f at the, let's say let's change the variable to u. This is going to be the summation from I equals 0 to infinity, and it was a polynomial in the variable u, and the coefficients came from the ith derivative of f evaluated at 0, and this was divided by I factorial. I'll just write in general here for points u near 0. For some functions, these power series, for some functions, these Taylor series were valid across the whole real numbers. For others, they were only valid in a certain interval around the base point or around the origin. So the beginning of this would look like, well, when I equals 0, you're just looking at the value of the function at 0. Okay, so by default or by convention, the 0th derivative of the function is just the function itself. And you haven't differentiated it. 0 factorial is 1, and u to the power 0 is 1. So you're just looking at the actual value of the function at 0. And then we had the first derivative of the function evaluated at 0 times u. Then the second derivative evaluated at 0 over 2 times u squared, and so on. Okay? So it gave us a polynomial, or a power series, an infinite polynomial in the variable u, which agreed with the function f of u, at least for points close to 0, some neighborhood around 0. And if you took any finite part of the power series, if you took any finite polynomial part, that would give you an approximation. And the more and more terms you take, the better and better the approximation becomes. Okay? And this idea of Taylor series and power series, it's very important. It gives you the way that functions are evaluated. I mean, how the computer or your calculator comes up with values for the sine function or cosine or the exponential function and so on. In the computer, at the bottom level of the circuitry and stuff, the computer doesn't know anything about triangles or exponentials and so on. You know, fundamentally, the computer can only add ones and zeros together. That's all the computer can do fundamentally. Okay? Now you can convert numbers into a binary representation. So adding ones and zeros, being able to, you know, remember the results and process the results. That's enough to add any numbers together. You can express any number in binary. And being able to do addition by, you can just do repeated addition then to carry out multiplication. So at a fundamental level, all the computer can really do is add together numbers and multiply numbers. So it doesn't have, a fundamental operation that can evaluate the sign function or evaluate an arbitrary function. Okay, but the fact that well-behaved functions can be approximated by polynomials like this. So to evaluate a polynomial, all you need to be able to do is add and multiply. Okay, because u squared, u cubed, and so on. That's just multiplication, and then you add them all together. Okay, so power series or Taylor series like this is the way to compute with machines, with computers, the values of arbitrary functions. Okay, so that was the one variable case. So coming back to, now we want to see what this looks like for functions of two variables. Okay, we can do a very similar thing, but it's going to look slightly different because there's more than one variable, right? So instead of derivatives of the function, we're going to be talking about partial derivatives. And this is how we set it up here. Okay, so we're going to talk about a two-variable case, but the same principles generalized to functions of more than two variables. So we're going to think of a function, what have I called it here, f of xy. And we'll be talking about a and b as the base points of the Taylor series. So there I was using 0, but in general you can evaluate it at any point. I'm going to write h and k. So h and k are playing the role of u in what we just wrote on the page. H is a small variation in the x variable, and k is a small variation in the y variable. So those are small variations of the base point AB for the x and y variable. Instead of the derivative appearing, the first derivative, second derivative, third derivative that was appearing in the one variable case, we talk about this differential operator d, and it's a combination, it's this linear combination of the two partial derivatives, h d dx plus k d dy. So this is a differential operator. I've got derivatives there, but I haven't said which function they're applied to. So I can take this combination d and I can apply it to a function. So when you apply d to a function f, d of f gives you h df dx plus k df dy. So d is that linear combination of the partial differentiation operators, d dx and d dy. So that would be d applied to f. Then you can also think of d squared applied to f. Now, if d is an operator, d squared does not refer to d multiplied by d. D squared refers to composing d with itself, taking d of f and then taking d of the result. That's what you get when you apply d squared to f. So see here, you apply d squared to f, d applies to f to give you what we have at the top, h df dx plus k df dy, and then the operator d applies again to it. Okay. Which leads you to this combination of second order partial derivatives. So you pick up a h squared d2f dx squared, a k squared d2f dy squared, and 2hk times d2f dx dy. The mixed second order partial derivative there at the end. And in turn, you could talk about d cubed of f, d to the power of 4 of f. Okay? These are the iterates, if you like, of d. D composed with itself applied to a single kind of argument function at the start. So this is what Taylor's theorem looks like then. And we'll look at some examples. We'll look at an example shortly. It looks very similar to the one variable case that you've got written on the page in front of you, with the notes that I just had on the screen. The same structure, but instead of the nth derivative or the ith derivative of the function f, here we've got the nth iterates of that differential operator. Okay? So again, it's this infinite series, sum from n equals 0 to infinity. There's two variables in the power series now, h and k. See, h and k are both in the definition of d. So in the right-hand summation here, you've got the variables h and k. So this is an infinite polynomial in h and k, power series in h and k. At each stage, for each value of the index n, you calculate the nth derivative of the differential operator d applied to f, and it's then evaluated at the base point. So d to the power n applied to f, and that's evaluated at ab. So that's the similar thing to the one variable case of having the ith derivative, as we just wrote down, evaluated at 0. So evaluated at the base point ab. And again, we have that factorial scaling thing at the front. It's 1 over n factorial at each stage. Okay. So if you looked at the first few terms of that series, again, this looks similar to the thing I wrote down on the page for the single variable case. F of AB plus d applied to f of AB plus 1 over 2 factorial applied to d squared f of AB, and so on. Okay. So let's jump in and look at an example. So we'll do example 1.11. Some of the results of the example are laid out there on the page, but we'll work through the details of it. Just to show you what we mean. Okay, so the function we're dealing with here is f of xy. That's the definition: sine of x plus 3y plus cosine of 3x plus y. And we wish to look at the first few terms of the Taylor series, about the base point pi over 2, 0. So the Taylor series about point pi over 2, 0. Then we just evaluate the various parts. So the first term, if you're looking at the expansion at the bottom of page 18, the first term we'll need is f of pi over 2, 0. That comes out equal to 1. Because the sine of pi over 2 is going to give us 1 there. Cosine of 3 pi over 2, of course, is going to be 0. Sorry, hang on. Sorry, I'm just going to bring these a moment. Sine of pi over 2, cosine of 3 pi over 2 is 0. That's right. So for d applied to f, then, this is going to be h df dx plus k df dy. So we need the two partial derivatives, df dx and df dy. So df dx, of course, is going to be cosine x plus 3y minus 3 times the sine of 3x plus y. Okay, so you can evaluate the partial derivative df dx as like that, and then df dy, a similar looking expression, except we'll have 3 times the cosine of x plus 3y. Minus the sine of 3x. Now we want these, in order to put these into the Taylor series, we need to evaluate these partial derivatives at the base point, pi over 2. Those are given there. When you take df dx, evaluate it at pi over 2, 0, 3. Because sine of 3 pi over 2 is going to be minus 1, so you get minus 1 times 3 plus 3, and df dy, evaluated at pi over 2, 0, you get minus minus 1 there, so you get plus. So this means that the second term, which is going to come in the Taylor series, is d applied to f, evaluated at the base point pi over 2, 0. There's no, well, there's a 1 over 1 factorial. Come to that if you like, that just leaves 1. This is going to be 3h plus k. So those are the order 1 term. For the indices in the variables h and k sum to 1. Those are the order 1 terms in the Taylor series. We can say, so the Taylor series begins, Taylor series for f about the point pi over 2, 0. This begins at f of pi over 2 plus h k. The constant value is 1. It's going to begin like this, 3h plus k. And then you're going to have further terms after that. So this is the linear approximation. This can also be called the linear part, the linear approximation. Approximation by plane defined by the equation z equals 1 plus 3h plus k. That will be the equation of the tangent plane to the surface defined by f at the base point pi over 2, 0. So that's the expression for the tangent plane. Tangent plane to the surface defined by f at the base point pi over 2, 0. Okay, so you can keep on going to calculate the higher and higher terms. So I mean, that's done in the notes there. It at least shows you the results. So you then have to look at capital D squared applied to f. Well, that's already worked out for you in equation 1.109, page 18. So it's that combination h d2 dx d2f dx squared plus k squared d2f dy squared plus 2hk d2f dx dy. You need to evaluate that expression at the base point pi over 2, 0. So you need those 3 second-order partial derivatives. To calculate those, you're continuing on the partial differentiation applied to the df dx and df dy. Work out what the expressions look like, evaluate them at the base point, and work out the second-order terms. So you can see it comes out to a combination of h squared, 6hk, and minus 9 squared, minus 9k squared. I'll show you what this will look like on getting MATLAB to help us with these. Because working these out by hand is, I mean, it's okay for getting the first or second order terms, but as soon as you're looking for higher order terms, I mean, if we had, in our original function, if there was an x squared or a y squared in here, inside the sine or cosine functions, if you ended up getting products of functions of x or y, so that you then had to use the product rule or the chain rule a number of times, as you went into the higher and higher order terms, your expressions for the derivatives will be getting longer and longer and longer. So it'll quickly become, you know, impractical to carry that out by hand. So I'll show you, or just show you a quick demonstration of how you can get MATLAB to help you in carrying out these calculations. So I'll just switch over to the computer very shortly now. Okay. So let's just look at how MATLAB could help us with this. So if we want to be talking about the variables x and y, we need to do a sims x and y to declare those as symbolic variables. And I'll take this example function from the notes. As soon as this comes back to me, might have been sleeping a bit. There we go. So I'll define this expression for f. So this is the example we were just working with. Cosine 3 star x plus y. And I want to talk about the variables h and k as well. So I'll get those as symbolic variables. So D, for instance, was diff fx plus diff fy. So that's the partial derivative of f with respect to x plus the partial derivative of f with respect to y, and we were multiplying h times the x derivative and k times the y derivative. So that line should show me the 3h plus k. Oh no, except I have to evaluate these at the base point pi over 2, 0. So that will put those values in for x and y. Pi over 2, 0. I hope it, or do you have to call it capital pi? It's complaining about my brackets there. Yeah, so it can, okay, I was getting error message, I wasn't quite giving it the right format there. So you can give us diff fx and diff fy. Actually, I think you need to do something like this. So I'm going to substitute into diff fx, I'm going to substitute for x and y. So I needed to use the subs command. So it wasn't understanding me when I was just trying to pass pi over 2, 0 into diff fx. I needed to use the substitute command. So this line here I just did, it works out the partial derivative of f with respect to x, and it then substitutes for the variables x and y the following values pi over 2 and 0. So that gives you the 3. So that 3 is, in the example, the 3 that's appearing before the h. And so if I do the same for instead differentiating with respect to the variable y, so I just change that x to a y there, that should give me just a 1. So that's the 1 that's appearing in front of the k. Now if you look at the note, when I went on to get the second order terms, you see in the equation 117, you have d2 applied to f, you get a minus h squared. So that minus h squared, that comes from taking the second order derivative of f with respect to x both times, which I think you get by just doing diff f and stick 2 x's after it. So diff f xx will take the second order partial derivative of f with respect to x, and substitute in these values pi over 2, 0 for x and y, and then it will evaluate that symbolic expression at them. That's what the subs command is doing. So you get the minus 1. So that minus 1 is the minus 1 that's appearing in front of h squared, h squared for the second order term in the Taylor series there. So by making use of this diff command for partial differentiation and the subs command, you can get MATLAB to carry out a lot of the hard lifting work for you, and as well to check and verify results that you've calculated by hand as well. Okay? Now this is week 4. Yeah. So I think in the lecture on Friday, I'll show you a few more examples of this as well, using MATLAB to do some things for us. Okay, so that's the first application we're looking at today. So Taylor series of functions of more than one variable, and there are tutorial questions based on those, which you'll find at the end of the chapter. It's going to bring us to the end of just the end of the section. So the second application is about so-called extreme values of functions of two variables. Or this is also called critical points. So these are the critical points on a surface So what we're doing here for functions of two or more variables, we're generalizing the way that we were able to optimize functions of a single variable. Okay, look at local maximums, local minimums, and points of inflection for functions of a single variable. So you'll remember that the surface was the equivalent thing of a graph of a function of one variable. So when you've got a function of two variables, it defines a surface. Okay? There's points in the xy plane. You think of the xy plane as being the ground. This relationship z equals fxy. You use the function to give you a height value above every point on the ground plane. And so as that height value varies smoothly across the points in the plane, that describes a surface. Lying above the plane for positive z values, or below the plane, below the level of the floor, if you like, for negative z values. So what do the kind of local optimum points on a surface like that look like? Okay. So to complete the sentence, the critical points on a surface defined by n equals f of xy come in three types. So you can have, the first type is local maximums. And you just think of a local maximum on a surface as like a point on the top of a hill. Okay? So the surface will be some kind of shape, and somewhere on the surface, it's a really bad picture. We'll look at some MATLAB pictures in a minute. But this point here is the top of the hill. Every point on the surface close to that point is got a lower z value. Okay. Or you can have local minimums. So this would be where the surface drops down into depression. So this is like the bottom of a depression. And what you get by taking your head and turning it upside down. It's the bottom of a well on the surface. Okay, my joint skills don't talk too much, but we'll look at some MATLAB spots in a moment. But there's a third type, and this in some ways is like the point of inflection. For the one variable case, we can have saddle points. And saddle points aren't quite maximums, they aren't quite minimums. They kind of display some of the behavior of both. And they're called saddle points after the characteristic shape of a horse's saddle. This is the underneath of the surface, you can see there, a bit here. Again, think of the Z vertical axis going up the page. See this point here, just on the center of the saddle, right where you sit on a horse's saddle. If you're sitting on a horse's saddle, and as you go left and right, you're sitting at a high point of the saddle. Okay? Your legs go down, the saddle goes down the horse's body to the left and right. But if you go forwards and backwards, you're sitting at a kind of a minimum point, okay? Because the saddle rises behind you and in front of you, like the shape of the horse's back rises to the horse's rear and to the horse's neck. Okay? So if you think of this characteristic saddle shape, if you're going back and forwards along here, it kind of looks like a minimum in this direction. But if you come to the left and right, either side of the saddle, it's acting here like a maximum. So it's kind of a mixture of the two types of behavior. So this is the third type of critical point we have for on a surface. So you've got the point at the top of the hill, where the surface comes to a hill shape, so that point on the top of the hill is the highest point in a certain neighborhood at that point. Okay, the function might get higher elsewhere, of course. That's a local maximum. Then you have the opposite of the top of the hill, you have the bottom of the depression. Okay, a place where the surface dips down, it's like at the bottom of a well, so on. And then these saddle points, which are mixtures of the two. Okay, and we would like to be able to do two things. We would like to be able to take the definition of a surface. So take a function that defines a surface, and we'd like to be able to find the stationary points and to classify them. So if we turn to definition 1.8, now that shows us how to do that. And it kind of looks slightly similar to the one variable case. The stationary points, I mean, what defines a stationary point or a critical point, the two types of terminology used, is these are the points where the first derivatives vanish. Okay, so where the two first derivatives are equal to 0. Or in other words, the tangent plane to the surface of that point is horizontal, parallel to the xy ground plane. Think about that. That's at the top of a hill, the tangent plane is going to be horizontal, parallel to the ground. So at the bottom of a depression, the tangent plane is going to be parallel to the ground as well. So that's how we find these stationary points. We search for solutions of these two equations here. The two equations in 1.121 there. The x derivative evaluated at the stationary point x0, y0 has to be 0, as well as the y derivative, df dy. That finds the stationary points, but we then need to be able to classify them into one of those three types. And the classification is carried out with the aid of the second order partial derivatives. Okay? Now, it's carried out using this quantity capital D. Capital D is better known as the Hessian determinant, the determinant of the Hessian matrix. The Hessian matrix, H of F, is this matrix of second order partial derivatives. So you've got fxx and fyy on the diagonal. Those are the second order partial derivatives with respect to x and y respectively on the diagonal. Then on the off diagonal, you've got the two mixed second order partial derivatives, df dx, d2f dx dy, and d2f dy dx. Of course, they are both the same, okay, for most reasonable functions. Okay. So once you have the stationary points x0, y0, you evaluate this determinant. So this determinant is this mixture of second order partial derivatives, and then you check the value of that Hessian determinant at the stationary point. If the Hessian determinant comes out negative, then the critical point is a saddle point. And if it comes out positive, you then have to go and check the value of Well, it's written here, you can check f(x), the second order x derivative. You can also check the second order y derivative. That will display the same behavior. You check the sign of that. If the second order x derivative is positive, then the stationary point is going to be a local minimum. And if it is negative, then the stationary point is going to be a local maximum. Okay. So there's an example carried out here in the notes. We'll look through this. And then we'll check or we'll verify the results by looking at the plot of the surface and using MATLAB. So we take a polynomial function. This is a kind of a order 3 polynomial in x and y. It's order 3 because of the terms x cubed and xy squared. Those are order 3 terms in x and y. So it's that polynomial. So that defines some kind of surface over the xy plane. And we're going to look for and classify its stationary points. So we find the two first order partial derivatives, df dx and df dy, and we consider them both equal to 0. And we're looking for the simultaneous solutions of these two equations. So a solution is a pair of values, a value for x and a value for y. A pair of values that simultaneously makes both the equations true, makes both the partial derivatives equal to 0. Now, when you're faced with this, I mean, in general, for general complicated functions, these are going to be nonlinear equations, so they may take a bit of careful thinking to solve. But the correct way to approach it is you're looking for the simultaneous solutions of two equations. So the way to do it is to focus on, say, the simpler of the two equations first. Focus on the simpler one and work out under what situations that first equation is true. Under what equations that partial derivative vanishes. Under what conditions. And then you take those conditions and you impose them on the second equation. Okay? So you're looking for a simultaneous solution. So whatever characterizes the truth of the first equation you look at, you have to impose those conditions onto the second equation. That should simplify the second equation, which you then get the final solutions out of for the variables. Okay? So let's look at how that appears for these two equations. So clearly the simpler of the two equations, I think, is the second one, 6xy minus 12 equals 0. Okay, it's got the fewest terms, and we've just got x times y and more terms. That looks a lot easier to try and work with initially than the x squared plus y squared minus a constant equation. So we focus on that first equation. That first equation, we can characterize the situations when it's true as being this relationship here. The second equation is true if and only if y is equal to 2 over x. Or equivalently, x is equal to 2 over y. But x and y must have this reciprocal relationship. Okay, y must be equal to 2 over x. That's the only way that equation 6xy minus 12 equals 0 can be true. Okay, you get that by taking the 12 over the other side and dividing both sides by 6x. Okay? So that relationship, y equals 2 over x, that characterizes the solutions to that second equation. So any stationary point must look like the x and y coordinates of the critical point. They must satisfy y equals 2 over x. It's not enough to be a critical point, because we've only looked at one of the equations. We're not saying that every point which satisfies y equals 2 over x is a critical point, but every critical point must appear there. So we take that relationship, then y equals 2 over x, and we impose that on the other equation by simply substituting for the y variable, substituting the expression 2 over x. That then gives you an equation in x only. When you simplify it a bit, it's on the second line there, it's looking like a quartic polynomial, 3x to the power 4. But of course, you only have an x to the power 4 and an x squared and a constant term. So although it looks like a quartic, it really isn't that complicated because it's just a quadratic in x squared. You've got x squared squared multiplied by 3 at the front, you've got x squared multiplied by minus 15, and then you've got a constant. So it's a quadratic in x squared, so you can use that kind of quadratic thinking how you solve quadratic equations. Here, we don't go to the quadratic formula because we notice a nice factorization of it. You can take out the 3, and then it factors, and you can see values of 1 and 4 for x squared. So out of that analysis, then you get 4 values for x. because you get plus and minus 1 and plus and minus 2. They're the values that make those two brackets 0. So plus or minus 1 and plus or minus 2 are your 4 possibilities for your x value, and then the y value comes from the relation that you found from looking at the first equation, that y must equal 2 over x. So you take the 2 minus 2 and the 1 minus 1 for the x, and then the relationship y equals 2 over x gives you the corresponding y value for each of those points. So those are your 4 critical points on the surface now. Now what types are they? Well, to get the types, we then pass to this expression D, the determinant of the Hessian matrix, that mixture of second-order partial derivatives. We calculate out those second-order partial derivatives, evaluate them at each of the critical points, okay, and we find these conclusions. The points 1, 2, and minus 1, minus 2 are both give negative Hessian determinant, so those are going to be saddle points. The other ones give positive Hessian determinant, but when you check the second-order f derivative, you get negative value for one, positive value for the other. Okay, so one of them is a local minimum, and the other one is a local maximum. Okay. So what I'd like to do now, in the couple of minutes just remaining, is just to quickly verify this using MATLAB and get a look at some of these points and see what they look like. So a good way of getting quick views of a surface is to use the easy surf command. And so the function defining this was x cubed plus 3 times x times y squared minus 15 times x minus 12 times y. If you type easy surf, that's a funny command. You pass the function name as a string. If you look up the help on EZ-surf, you pass the function definition as a string to that. And then you can follow it by an array of 4 values. And these are the minimum and maximum for the x coordinate, followed by the minimum and maximum for the y coordinate. Now these points are all around x equals 1 and x equals 2 and y equals 1 and y equals 2. So I'll plot the thing over the grid extending from minus 3 to plus 3 for x and the y variable. That will capture within it all 4 of the stationary points. Okay.
You put 4 times x times y squared in the equation. It says x cubed plus 4 plus 3.
It's x cubed plus 3, isn't it? So I got the wrong. Is that right? So replace the 4 with the 3. Thank you. Where's my cursor gone? Oh, it's just working extremely slowly. Okay, so there's the surface. Oh, I need to correct it, don't I? So close that. So that 4 becomes a 3, isn't that right? X cubed plus 3 minus 15 minus 12. Okay. Okay, there's the surface. Now, when we're looking at it at that scale, we've got all 4 of the stationary points. You can see the x and y coordinates. So you can look to where each of the critical points are. It's maybe not that easy to appreciate the nature of them from that graph, from that surface, but I'll zoom in on 1 or 2 of them now. But you can kind of see that maybe down here at the front left, there's a top of a hill. There at the back right, there's a bottom of a depression, and then located beside them either points, there are these saddle points. But again, because the whole thing isn't varying much in height, it's not so easy to appreciate it. So just to see that more clearly, I'll just recenter the plot so that we're just looking at one of the critical points. So let's choose one of the saddles. So there's a saddle located at the point 1, 2. You can see from the solution. So I'll recenter the plot So I'll go from 1/2 to 1.5. That will be centered at x equals 1. And from 1.5 to 2.5, that will center it at 2 on the y-coordinate. So this should look very clearly like this characteristic saddle shape, horse's saddle. You can see it does there. You can see that point in the center of the surface. Get a nice view of it. So the point in the middle of the surface, as you go backwards to the left and forwards to the right, the surface is rising in value. That's like going forwards and backwards along the horse from the middle of its back. But as you go to the front left and the back right, you see the surface is falling away. So in that direction, the point is acting like a maximum. Okay. And if you recenter the surface plot around each of the other 4 points, you can get a good view. Because you're looking closer at the point, the nature of it becomes more pronounced and you can appreciate it from the surface plot. Okay, so when I see you later, next time, we will do far more practice with this. So I'd like you to collect, I'll have them down here, I'll make a couple of files down here, but this is the coursework assignment. So we're handing this out now. So I'll put a bunch of them here, put another bunch over on this table. Let me take one of those.